Hello, everyone. My name is Itote. I'm here at Chemnitz University of Technology, and it's a great pleasure to be here talking about my research. Over the last 2 years, I've been working on developing on-robot proximity sensors and how to use these sensors to control the robot. On-robot proximity sensors are proximity sensors that are attached to the robot's outer surface, and they provide information about the presence of obstacles in the robot close proximity. And I will show you how to use this information to create reactive avoidance motions for obstacle avoidance and how to proactively reduce impact forces. In today's talk, we'll cover a relatively large field, starting from sensor design to the control algorithms. But I find this topic very interesting, and I hope you'll find it too after my talk. I'll try to provide all the detailed information for the committee and also try to make it very interesting for everybody else who's not that familiar with this topic. I want to start with the concept of proximity perception. Proximity perception uses the inside-out view concept, and compared to external view cameras, they don't experience occlusion in the same way. In fact, anything that occludes the sensor is a relevant obstacle. And otherwise, the sensor remains untriggered. With that, we can achieve very low latency and very fast update rates. And this is important for fast reactions of the robot. Furthermore, we can preserve privacy. Another point is that proximity always precedes touch. We can react earlier before impacts occur. In this example, with even low, small detection distances, we can reduce impact forces very effectively. Or from another perspective, the robot can move much faster while still maintaining the safety of force limits for safe human-robot interaction. And with that said, my research in proximity perception is related to safety in human-robot collaboration. On the left, you see a typical industrial setup where the environment of the workspace is where the workspace of the robot is very well defined and well known for repetitive and pre-programmed motions. And therefore, the workspace is fenced to avoid disturbances by humans and protect them. On the right side, in contrast, we see an application that's called collaborative robots. Cobots are designed specifically for human-robot interaction, where the robots and the humans share the same workspace and interact with each other. Now, cobots have some safety features, and from a mechanical standpoint, they're typically very lightweight. They have soft paddings and rounded corners. They also use some kind of sensor systems to provide further safety. For example, they are compliant and soft through the use of force and tactile sensing, and they also use external viewing cameras to detect intrusion into the workspace. And often the reaction is a simple issuing of a safety stop or the reduction of velocity. Now, the problem is with these two sensing systems that there's a perception gap and the close proximity of the robot, where the vision can be blocked by an obstacle and where the tactile sensors or force sensors still remain untriggered. Furthermore, the control schemes still rely on today's industrial robot controllers, which are simple motion automata that strictly follow a predefined path. Predefined motions are very unsuitable for cobots to move in a cluttered environment, where everything is continuously changing and without risking the safety of humans or damaging the robot itself. And we can solve this problem using on-robot proximity sensors to bridge the perception gap and can use this information to go beyond simple stopping or reduction of velocity motions and use more sophisticated motion generators to create reactive motions around obstacles or use them to attenuate impacts. So today's talk will cover the main 3 contributions of my work, which cover the complete perception action loop. First, I will give a short introduction and brief overview of my self-developed sensor system. Then we'll jump over to the generation of motion generation part for obstacle avoidance. And then we'll discuss how we can proactively reduce impact forces. The system that I have developed looks like this. And fun fact, the main intention of my work was originally to focus on the motion generation part. However, there were no systems available. So I had to develop a system by myself that is able to detect humans robustly and also provide sufficient information for the control algorithms. The system consists of 3 sensing cuffs. They are attached to the 3 main links of the robot, and each of these cuffs house different numbers of proximity sensing modules, which are the heart of the system. Each sensing module uses laser time of flight sensor for far range detection, and also uses a self-developed capacitive proximity sensor for wide area coverage of the robot. And this is important in case something slips through the view of the laser time of flight sensor, and then the capacitive sensor is still able to detect them. The complete system looks like this. We have some kind of motion input, which can come from capture devices or some kind of higher level path planners. And the desired motion goes into the robot control algorithm, which considers the sensor measurements from our proximity sensors and then generates a new joint motion, which is sent to the robot controller, where the motion is executed by the robot. I want to focus on the 2 sensing principles that I'm using. In the top left, you see the time of flight sensor that I'm using, which can be bought. And then in the top right, the self-developed capacitive proximity sensor. In this table on the left side, you see some sensing properties in which at least one of the sensors should be good at. Now I won't discuss all the properties because of time. So let's start with the range. The time of flight sensor has very good range, up to 1 meter in this case, and very high accuracy due to absolute distance readings. Proximity sensors, on the other hand, have very low sensing ranges, or small sensing ranges. And also the distance readings are not very accurate because they are material dependent, also depend on the target sizes. And an interesting point is that time of flight sensors don't have that much update rate in the range of 30 Hertz to 100 Hertz. But this is not very important because of the large sensing range, where with the large sensing range, we can react very early to obstacles. With the capacitive sensor, on the other hand, we need very high update rates because we have to react very fast due to the short sensing distance. Now, what's most interesting is that time of flight sensors have difficulties in detecting black and transparent objects or reflective objects. And this property is not applicable to capacitive proximity sensors because they only rely on the material internal electrical properties. Now, capacitive sensors have difficulties in detecting materials that are low in permittivity and time of flight sensors. And this is not applicable for time of flight sensors. So they kind of compensate each other's weaknesses. However, there's a worst case scenario where the target can be made of black, transparent, reflective material, and at the same time, where the material is very low has very low permittivity. And this is usually the case for some kinds of plastic materials. I want to highlight some kind of, before we go to the next one. However, the main focus on the sensor system is to detect humans, and usually one of the sensors is able to detect humans reliably. I also want to highlight the sensing principle I have developed myself. Usually, the capacitive sensors use one of these 2 sensing principles shown here. And the problem is with the grounded state of the target. If the target is grounded or ungrounded, the sensor readings will be different. And this can be seen here in the plot. For the grounded target, we have the same sensor readings for 20 centimeters as for an ungrounded target at 1 centimeters. So if we don't know the grounded state of the target, this sensor readings is very unreliable and actually very not very useful to use. I solved this problem through a self-developed sensing principle. This is very similar to the mutual capacitance method. The only difference is that the second electrode, grounding electrode, is now driven differentially, which means the signals will cancel each other out in the object itself, and the voltage inside the object will always be 0. And therefore, we can virtually ground the object. It is always grounded. And as we can see in the sensor readings with the differential signal, no matter if it's grounded or ungrounded, the sensor readings are very, very similar. With that, we can achieve reliable proximity measurements, no matter how the target is grounded. Summarize everything, I've developed a laser-based time of flight or sensor module that uses laser-based time of flight sensing for far range and capacitive sensing for wide area coverage. The sensor principles compensate each other for their sensing weaknesses, and we have robust detection of humans through capacitive sensing. Okay, we have fast update rates, and now I have finished giving a short overview of my on-orbit proximity sensors, and we jump over to the next part about reactive motion generation for obstacle avoidance. If you couldn't follow before, now you have your chance to step into the game again. Yeah. If you want to move from point A to point B and are given 3 paths, and ask a path planning algorithm which would be the shortest path, it will provide us information that green line will be the most shortest line, because it considers all the every information it has in the environment. What about if we only have limited perception, or even worse, we can only look ahead 1 step ahead, and this resembles reactive motions. We will look or try to optimize for 1 step ahead and find a motion that is most suitable. And the idea for this part is that global planning or planning algorithms provide very good results, the most optimal results, but require a lot of information and computation time. And this is not very suitable if, for example, someone jumps to the robot and you need to change the robot's motion and be very reactive. And we can use reactive motions, which don't require a lot of sensing information and also have very low computation times to generate reactive motions. With that, we can keep the robot in a safe state while the global planning process is still running, and we buy some time for the global planning algorithms. The objectives of the reactive motions in this case are to have contactless multiple obstacle avoidance for the complete arm, want to be very fast, want to fill the time gap between detection and replanning, be less restrictive than commonly available motion generators, and want to fully use the robot's redundancy to maintain the desired motion or robot task as long as possible. And before we start with the avoidance motion generation, we first have to know how we can control the robot, right? Usually the avoidance motion is given in a vector in the task space or Cartesian space. And we need to find a mapping function that maps our task space motion to the joint space motion, because the manipulator is usually controlled by the joints. And the mapping function which does that is the Jacobian. The Jacobian is the derivative of the position and orientation of a certain point on the manipulator with respect to joint angles. And with that, we can calculate the task space motion for a given joint motion. And usually we require the inverse of that. We command a task space motion and need the joint space motion to control the robot. So therefore, we can invert the Jacobian to get that. Now, very often the Jacobian is not invertible. For example, if we have redundancy, more joints than necessary, or if we don't have sufficient joints to execute the task. Now we can use the following pseudo-inverse solution, and without further proof, before it will take too much time, this pseudo-inverse minimizes the quadratic error of our joint task space motion. We can apply that, and the robot will move to a specific target position. We can further extend this motion through task priorities and redundancy so that the robot is allowed or can move to two separate directions at two separate points. This can be done with the following quadratic cost function, where we have in the minimization term the secondary task, and in the constraint the primary task, so they are prioritized. And if we solve this through quadratic optimization, we get this following solution, and if we apply that to the robot, we can now task the robot to move into a separate direction. And with that, we can already implement a very simple avoidance motion generation algorithm, which is just to ask the robot to move in the opposite direction of the obstacle. And with that, we can still see that the robot can move its main task, while in the secondary task, the robot is able to avoid obstacles or even switch. Sometimes the avoidance motion can be also as the main task. However, repulsive motions are very, very restricted because you ask the robot to move in the opposite direction. And this can cause problems in terms of in front of obstacles, because the robot can freeze before them. And this is because the repulsive motion and the attraction motion to the target or to the target position, they cancel each other out. Therefore, the robot freezes in front. Now, in order to solve that, we can be less restrictive. What if you only ask the robot or define a plane and let the robot decide on its own which direction to take? And this is less restrictive, and the robot is able to move around obstacles. And we can be even further less restrictive by defining a space in which the robot is allowed to find an optimal solution. And we only constrain this space towards the obstacle where the robot is not allowed to move. And this would be the second strategy we will discuss. First, the first strategy, the sideways motion. On top left, you see the distance towards the obstacle. And if an object is in this range, in first range, there's no interference to the robot's motion because it's far away. As it gets closer, you apply avoidance motion as lower priority task so that the robot task is not affected. And if it gets even closer, we switch priority of the avoidance task with the robot main task. And that way, the main task is executed by 100%, while the robot tries to perform its robot task. And if that is not sufficient, we apply repulsive motion, which allows us to guarantee contact-freeness of the robot. Now, the way we choose our avoidance vector is through sampling. And this orthogonal plane is defined, or this plane is orthogonal is defined as orthogonal plane in the direction of the obstacle. And we sample around different positions or vectors for different scores and choose the avoidance vector with the best score as our avoidance vector. And the scores look like this. We have first the error of our secondary task motion, which can be, depending on the situation, the main task or the avoidance task. And we have the distance towards the obstacle, the manipulability, or where the robot can move for a certain position, and acceleration. We can then calculate the total score from all of these scores, and 2 of these scores are multiplied because they are more important. We have manipulability. You want the robot to move to a direction where the manipulability is not 0. Otherwise, the robot cannot move anymore. And this is not good for obstacle avoidance. And we also, and the distance towards obstacles is also very important. So if one of these scores is 0, the complete total score will be 0. And the other scores, they are not that important. So that's because we just add them. Now, for the second strategy, I tried to summarize everything into one general framework by using constraint-based quadratic optimization. First, we have here our quadratic term, or cost function, where the first term describes our main task, then the error of our main task. Then we have here the velocity, since we want to reduce joint velocities so that we can avoid singularities. And we have here forces required for the motion. Now, the quadratic optimization tool will try to minimize this cost function. However, here, there's still no avoidance strategy implemented, or avoidance motion implemented. And this is done through constraints. We can calculate for each point that is closest to the obstacle on the manipulator, the motion towards the obstacle. And we can use a constraint to limit this motion towards the obstacle. And the constraint is defined as in the following graph. If the obstacle is far away, there's no interference or no constraint. And if the obstacle comes closer, the speed allowed towards this obstacle is reduced linearly. And if we go beyond a certain threshold, then this allowed speed towards the obstacle becomes negative, which means the motion of the manipulator or of this point has to have some components in the opposite direction. And if you have further obstacles, then you can add them up or summarize them as a vector in constraints. And this is the solution, or this is the result. Here we see the traditional repulsive motion where the robot gets stuck in front of an obstacle. Now we can see, it's stuck. Now we can see that the robot is able to move around the obstacle. And if the obstacle disturbs one of the lower links, the robot tries to maintain its main task. Now I have discussed reactive motion generation. We jump over to the next part, proactive impact attenuation. Now there are situations where collisions cannot be avoided anymore. For example, if someone jumps very quick to the robot and the required motion for collision avoidance cannot be performed by the robot itself because of joint limitations. Well, there will be impact, and usually the impact forces are reduced through the compliant behavior of the robots with impedance controllers. The problem with impedance controllers is that you cannot achieve accuracy and performance at the same time. If you're very stiff, you have to move slow because you have to reduce impact forces. And if you want to move very fast, you have to be soft. And therefore you can't have accuracy and performance. Now, the objectives are to remove the control paradigm restrictions of traditional impedance controllers. We want to increase safety and accuracy and performance just as required. We can use the proximity information to modify the stiffness of the robot just as required. For example, if the robot is in regular operation, then the robot can be very stiff and very accurate. And if something gets very close, the stiffness can be reduced just as required. We can also reconfigure the robot before the impact, just so that the robot joints can align towards the impact direction. And this increases the effectiveness of the joints. The impedance modulation itself is very simple. The closer an obstacle gets, the lower the stiffness of the joints. And this is controlled through the following diagram. Controller. We have this because we want to have different rates for stiffness increase and decrease. For decrease, we want to be very fast, and for stiffness increase, want to be more slower. And there's also an energy tank for stability. The problem is that if you push on the robot or deviate the robot, it's like a spring system where you compress a spring. And if you modulate the spring stiffness suddenly to a higher stiffness, then at the same compression, you have suddenly more energy or potential energy in your system. And if you have more potential energy in your system, suddenly, that means the system can become unstable. And this energy tank is used to provide the energy for stiffness increase. And if the energy tank is empty, the increase is not allowed anymore. So therefore, we allow some kind of unstable or dynamic behavior until the tank is empty, and therefore we can still remain stable. Furthermore, we can calculate a manipulability score, how well the robot is able to move towards the impact direction at the impact point. We can also calculate the effective inertia towards this impact direction at the impact point. And then we can use quadratic optimization again to calculate for a joint motion that allows us to decrease effective inertia or increase manipulability. And the result looks like this. Without any proximity information, the robot is very stiff and it's not able to reduce or dampen the impact. Now we can react very fast and change the robot stiffness just as required. And also the robot moves its joints towards the impact direction so that more joints can participate in attenuating the impact or damping the impact. To conclude everything, I have shown an effective last safety layer when collisions cannot be avoided anymore. We are very fast, and we can easily integrate the system or this into existing systems just by adding proximity detection capabilities. We overcome the accuracy and speed limitations of pure impedance controllers, and this should also work in combination with collision avoidance as last safety net. However, we have to take care with reconfiguration motions because during contact, the human is often very close to the robot, and we have to limit the range of motions for the reconfiguration to avoid injuries. To recap today's talk, in the perception domain, I've shown a self-developed sensing system based on two sensing principles. We can robustly detect humans or grounded and ungrounded targets. And we have also sufficient range. And we are very fast. For the reactive obstacle avoidance part, I've proposed two avoidance algorithms, which includes whole body and multi-obstacles. We also fully use the robust redundancy, and I've shown a formulation of a general framework for reactive obstacle avoidance. And in the proactive impact attenuation part, as I said before, I've provided last safety layer to reduce injuries, and we can also increase the accuracy and performance at the same time, or just as required. What's next? In the sensor system domain, we can investigate more into the shapes and sizes of capacitive electrodes. We can investigate methods and processes to integrate these into existing systems. And we can also perform sensor fusion with vision and tactile information. I've also done some work in material detection with capacitive sensors. In reactive motion car, we can integrate replanning or path planning. And aside from safety, we have also many more applications. For example, manipulation and grasping. We can have it as assistance systems for remote control, medical robots, and we can also perform exploration. So I'm done with my presentation. I'm really looking forward to the Q&A session, which will start right now. I'm happy to answer questions that just do. So thank you very much.